Hi, my name is Leo and I'm a master student on Aarhus University. On behalf of myself, Valentina Beatini and Poul Henning Kirkegaard, I'll be presenting a retractable roof pavilion. With our origami-inspired structure, we try to create a foldable structure through architectural engineering. We want to transform space, create versatility, and as such fit our sustainability paradigm. Through folding we also get form resistance. This is boldly explained on the pictures to your right. Within our tectonic aim, we try to be as conscious as possible when we are joining elements. We want, in other words, to enhance the structure as a whole. We work multidisciplinary and we have a flat organizational structure. The process has been iterative and we go through conception, design, and at last we use materialization and gestures to bring together elements. Here is a midway sketch of the pavilion. And early in the process, it was chosen to go with a mast for the support. This was done to offer minimal distraction for the audience, but also pointing out, or say by the height, highlighting the existence of this roof. The roof consists of these four identical elements, and the elements are interlinked by pistons. All elements are equally supported by rope in the circumference and rods in the inner circle. Interestingly, if we look at the variation of length, the inner rods elongate quite a lot, also being the activating part of the system, while the pistons and the roof radius remains relatively unchanged. When designing for foldability, you must consider the hinging method. Here we have three candidates: a traditional steel hinge, a compliant joint where the material is continuous but weakened where you want it to fold, or this third option with layering and integrated elastic joints. This offers a large rotational interval. It is also lightweight and the elements can be exchanged, which offers higher robustness than the alternatives. The rubber joints are manufactured by machine cutting, and all the plates, including the inverse pattern in the middle layer, is done by laser cutting. This offers high precision and low production time. We've increased the spacing between the rubber joint where it was possible in order to increase the moment capacity of the system. Regarding the materials, plywood was chosen for the outer layers for its structural properties, and HDF, high density fiberboard, was chosen for the middle layer to get the structure as thin as possible. The rubber hinges are tested in a transversal stress test, and we try to balance the shape between two yielding shapes. This one being a tension failure and this one being a sliding failure. You can see the iterative process down here and how the shape gets even more complex as we increase in iterations. On these photos you get a sense of the early manufacturing process, the laser cutting, the sorting of plates, and the weighing of plates to ensure the competition weight requirements. When all the plates were manufactured, it was time for assembly. And to your right, you can see the 4 quarters fully assembled and laying upside down on the floor in our lab. For the substructure, you might choose amongst different materials, and here are some materials and the related arguments. We've chosen bamboo above others, and I want to emphasize the low-tech qualities of bamboo, that we avoid over-constructing, and at the same time we create an architectural contrast to the high-tech appearance of the roof. Here is the first sketch of the joinery inspired from traditional bamboo crafting, and as you can see we've used C-cell for tensioning in the system. This is then the final joinery, and as you can see here, this is how we section the bamboo so we can get short elements and still reach our height of 5 meters. The roof is a single degree of freedom kinematic structure, and the motion that you can see here is controlled by actuators. Interestingly, we need a two-directional control, so two actuators, and these work interdependent with different function. This is because the motion of the roof is not linear, but actually curved. So at some point, one actuator is not enough because the roof motion will not need extension in that direction anymore. The actuators, or extendable connections, were designed in collaboration with our technicians. They have a function length of approximately 1 meter, and it's a homebrewed actuator from stepper motor and lead screws. The hardware is controlled by an Arduino script, and this is called in a sense a master and slave system, where one master Arduino board is keeping track of all the slaves, being the Arduino boards for each stepper motor. Here are some photos of the joinery that was made for this. Here you can see some process pictures from the assembly. We've made this scaffolding which allows us to raise the roof quarters and fixate them temporarily while the others are mounted. Here you get a vertical pan of the pavilion at its current stage. Thank you for listening. I'd like to thank my co-authors Valentina Beatini and Poul Henning Kirkegaard, as well as the technicians and my friends and family who also helped with the assembly process. Please follow the progress of this project on the link below, and I'll be ready for some questions.